All right, so this is where we got to last time. So we were on the road to deriving the leading order SCT Lagrangian. We said that there were some things that we had to deal with, in particular expanding it. And we started out as a first step getting rid of two of the components of the field that we said are not going to be ones that we project onto in the high energy limit. And that led us to this Lagrangian right here. But we haven't yet expanded it. We haven't yet separated the ultrasoft and collinear momenta or the ultrasoft and collinear gauge fields. And so in order to do that, I argued that you have to make a multipole expansion. And I talked a little bit about what the multipole expansion would look like in position space. And then I said it's better for us to do it in momentum space, and we started to do that, and we're going to continue to do that today. So first of all, let's just go to momentum space. So I've called the field here, since it's not the final field that we want, I introduced a crummy notation for it, Cn hat. And we'll just, once we get to the final field, it won't have a hat, and that'll be the one that we keep using from then on. So let's take this hatted guy, which is not the final guy, Fourier transform him, and talk about doing things in momentum space. In momentum space, I'm going to make an analogy with what we did in HQET. In HQET, we split the momentum into two pieces. We had a piece that was large and a piece that was small, and then we could expand. I'm going to do the same thing here, split it into a large piece and a small piece, where I'll call the large pieces the one in the lambda components, and then the small piece will just be all the pieces that are of order lambda squared. So if you draw a picture for this, it looks as follows. How should I think about what I'm doing here? Here's how I want you to think about it. So let's draw a two-dimensional picture in minus perp space. In plus space, there's no split because there's no plus here. So it's really in the minus and the perp space that we have to make a split. Yeah, let's see. All right. So I'm going to draw a grid. And the way I want to make this split precise is I'm going to think, OK, so I should have maybe made my axes in a different color to distinguish them from the grid. Let's make them orange. So the way I want to think about these two types of momenta is I'm going to think about these PLs as discrete and the PRs as continuous. So let's think about the PLs as labeling these points at the center of each of these boxes in the grid. This one was supposed to be in the my squares are not the same size, but they roughly should be. And so then we can think about if we specify some momentum in the space, let's say we specify a momentum that points to like this point right here, the way that I can point to that point is I take one vector that points to the center, and then I take another small vector that points to that point. The large vector is the PL, the small vector is the PR. OK, so this guy here is PL. Maybe I should make the other one a different color. PR. And so the way that we should think about this is in the following sense. We should think about the average spacing in between these grid points here as something that gets a power counting that makes it of order Q lambda. And the average spacing between grid points in this direction is something that makes it order 1. But if I ask about distances inside a box, if I ask about a distance like this one, that's of order lambda squared. OK, so to get between boxes, you need to make a big jump with a larger momentum. But to move around in a box, that's only small momenta.
So why can't you have order lambda basically inside the box in the p minus direction?
Yeah, so you could. So you can ask where is an order lambda momentum in the p minus?
Yep.
and it's in a netherland. So you can either think about it as being, either way, you can think about it as being part of this one or that one. It doesn't matter, because technically there's no, if I just talked about minus, I could, I'd only be interested in separating a 1 and a lambda squared. And whether I call this lambda squared or I call it lambda or I call it eta, let eta equal lambda squared, I'm only trying to separate two things. So if you talk about some momentum that's in between, you could ask the same question actually, but what about a lambda to the 3/2 momentum in the perp space? And that's the same question you just asked about the minus space, right? And that's something that we don't really care about, because there's not going to be momenta that are scaling like that. So we don't really care about separating it. Okay, so PL are discrete grid points, and PR are continuous And this picture also makes clear that if you take any P, it uniquely is given by some PL and some PR. If I point at any place in this grid, you can tell me exactly which PL I should pick and then what PR I should pick. This is in some ways just going to be a tool, and we'll see, and in the end of the day, we can kind of dispense with this picture, but it'll be a useful way of thinking about what's going on and getting to sort of the final results that allow us to dispense with this picture. So what about integration? So if I integrate over all P, and P is collinear, what does that mean? So it corresponds to summing over all the grid points and then integrating over all the residuals. Except for one location, and that's the special box here that has label equals 0, because we know that the power counting of the collinear momentum is such that it always has to have a non-zero PL. And so the one box where PL is equal to 0, 0, that particular box is not collinear, doesn't have a collinear momentum. And actually, that box is exactly what you think of as the ultrasoft momentum. So if you have an integral d4p and p is ultrasoft, there's no sum, and you just have integral d4pr, and that's like integrating over the 0, 0 location in the grid. Okay, so you can see that together we cover all possible places for an integration, and we actually don't do any double counting with this setup. What am I going to do with my fields? Well, because of this split into two different pieces, I'm going to say that my fields actually can be labeled by PL and carry PR also as a index or be a function of PR. So in order to make this explicit, we're going to write our Fourier transform guy with a label PL and an argument PR, like that. So the name label comes from the fact that we do this. And there'll be some analogies with why we called this a label in HQET. We'll see to what extent that analogy carries through in a minute. Another thing you should note from this grid picture is that you have separate momentum conservation in the label and the residual. So if you think about some integral d4x of something that you split between label pieces and residual pieces, then the right way of thinking about this is that you have a discrete chronic of delta for the label, and then a continuous Dirac delta for the continuous variables. There's some 2 pi's. And so this is what would be meant by if you have 2 momentum that are equal, you know that they're in the same grid square, and then they have the same little green arrow as well. Okay, that's what that's saying. So when we talked about what happens with the multipolar expansion in position space, we said that effectively you have a non-conservation of momenta. Okay, we had a field at 0, we worked through what that meant, and it meant basically that the momentum was conserved on the other line, but not on the one that you were doing the expansion on. The nice thing about this type of setup is that we have conservation of momenta, but we actually have 2 conservations of momenta. So we don't give up momentum conservation, it's just that we go over to a picture where we have 2 of them. So let me show you how that works. Let's say we have an ultrasoft particle, and it's hitting a collinear quark. The collinear quark, because it's collinear, carries 2 types of momentum. It carries a label P and a residual. But the ultrasoft guy only it's only residual. So let's just call that K residual. There's no label to that ultrasoft guy. So if I just look then what this guy's momentum is, it's P label for the large piece, because that is not affected by the ultrasoft guy, and then it's P residual plus K residual. Okay, so we have a conservation in the residual space, which is the standard one, and we have a conservation in the label space, but the ultrasoft particles just don't contribute to that. So we have 2 conservation laws. And we just know that certain fields can carry these label momentum and other fields can't. Okay. All right. Well, since PR here and KR, the residual components, is just like standard quantum field theory. The only thing that's special is the PL. For the PR, what we're going to do for the residual momenta is we're going to transform back to position space. And that's kind of what we do in HQET as well, right? We treat this guy as in momentum space as a label, and this guy is in position space for the residual. And the reason we really want to do that is related to locality, and I'll say some more words about that. Yeah. Sure. Yeah.
So are you bounding the D4 PR by lambda squared, or is there some reason why the integral should fall off before you get there or something?
Yeah, we're going to talk about that. So far, this is just notation. You could think of it, if you think about it from this grid picture, you'd think about some hard walls put in. That's not quite the right way of thinking about it. It's actually not right for several reasons. But we'll talk, and we will come back and talk much more about what the right way of thinking about it is. But the physical picture that you're in this box is the right way of thinking about it. The tricky thing is that these boxes are infinite. Each of these boxes is infinite. And we'll have to see why that is. In what I've told you so far, you'd think that the D4 PR would really be a box with some fixed edges. And it's going to turn out that the D4 PR, we're going to use dimensional regularization, it's going to be an infinite box. But we're still going to be able to do exactly what I'm telling you. And it's going to make sense. We're going to want infinite boxes to avoid breaking symmetries like gauge symmetry and Lorentz symmetry. And we'll come back and see how that works. So in some sense, what I've told you is a Wilsonian story. and we're going to have to make it into a more continuum-friendly story. But the moral of the story, of the way you think about where these momentum modes live, what kind of momentum they carry, that is just true. So that part of the story, which you can think of so far as Wilsonian, is true, and it's okay to think like that. So we'll see actually what we do in practice a little later on. Where this will really come in is when we start wanting to think about doing loops, but we won't get there for a little while yet. So the conservation law in the residual just corresponds to locality. We learned all about locality yesterday in Nima's seminar. And so we can make things local by just going back to the x space for the residual momenta. Okay, so we go back to the x space, which is the Fourier transform conjugate variable to the residual momenta. So the fields we're actually going to use are these ones, where we Fourier transform back in the residual. These guys here. Okay, so it's kind of like HQET, where you think about this part in momentum space and that part in position space. Okay, so if you talk about ultrasoft interactions, if you can see it from over there, they conserve the labels. So there's label conservation of a field for ultrasoft interactions. The label of the field here is the same as the label of the field there, so that ultrasoft guys do not change labels. So this is PL, this is PL, and if this is ultrasoft, it's still labeled by PL, and the thing that can change is the residual momentum, and that's now encoded in locality and saying these fields all sit at the same point x. On the other hand, the collinear gluons cause us to hop between boxes. So the collinear gluons are label changing. And that's what's different than HQET. In HQET, we don't really have interactions in the theory in the Lagrangian that do that, but here we do. So if we have a collinear gluon come in, the collinear gluon again carries both labels and residuals. If I just draw the labels, this is some QL coming in, and this will be PL plus QL. And so the label of the outgoing field is changed. There's one more label, and that's this N, right? We also label these guys by a direction. And that is unchanged also by the collinear interactions. So it's preserved by both ultrasoft and collinear interactions. It can only be changed by hard interactions, where you would have some hard production that could produce, say, two guys in two different directions. And those type of interactions are typically only going to occur once in your quantum field theory, kind of like a decay, a weak decay, where it occurs once, and then you do perturbation theory around that. Hard interactions are that way too. So as far as dynamics is concerned, this label N is something that you can think of as being conserved for the fields. It's not going to be changed by the Lagrangian, for example. All right. Okay, so now we have kind of what we want. And now I want to write the action that we had before in terms of this guy and see what it looks like. And that this split of these guys into a PL and PR or PL and X allows us to expand very easily in momenta. It's allowing us to do the multipole expansion. Because we have two things to talk about and we just can compare them. So let's put the pieces together. So Cn hat of X is the Fourier transform, full Fourier transform of this Cn twiddle. And that can be split for a linear guy. We can split the measure, and we can split the phase, and we can write the field in this way. And then we decided that we wanted to use this field, and so that, I'm missing some 2 pi's here. So that means we take this measure, we take this phase, we take this guy, and we write it back in terms of that field. So that leaves, if we want to relate the field that our Lagrangian was in terms of this field that I told you we're going to use, it's this equation. Okay. All right. A little bit more formalism. So we're going to actually want to have 2 different types of derivatives. Derivatives that can talk to the momentum conjugate to X, and derivatives that give this PL. So we define 2 types of derivative operators. One is just, if you like, a standard derivative in the X space of this guy, acts only on that coordinate. And that derivative scales like lambda squared. So that's residual. Talking to residual momenta. Then we need something that can give us the labels. So we define an operator that does that, which we'll call curly P. It doesn't care about X, and it's just defined to give the PL mu of the field it acts on. So there's no plus component to this. There's an order 1 minus component, and then perp, it's order lambda. I want to say how big that guy is. So then we have a power counting that tells us how big the P is and how big the partial is, and we can compare them and we can expand them. Okay, so the bottom line is that we now can just say that we have a comparison, like we had a comparison for the gauge field, we have a comparison for derivatives. Okay. And so this is exactly analogous to what we said before, where we had n bar at A ultrasoft being much less than n bar at A collinear, and A perp ultrasoft being much less than A perp collinear. And in fact, the way we're setting things up is going to make the gauge symmetry also easy, because by gauge symmetry, these derivatives and these fields should go together. They are the same size in the power counting, and these guys should go with those guys. Okay, so we're kind of doing this same thing we've thought of for fields, we're doing for momenta here. So when we talk about gauge symmetry, this will make Gauge symmetry easier. This homogeneity between the derivatives and the gauge fields. So that's one of the powers of thinking like this. Okay, so let's see that this notation is actually kind of friendly. So let me try to convince you of that. It looks kind of daunting, but maybe it's not so daunting. So let's look at this guy, which was equal to this. So what I can do is I can take this and replace it by e to the minus I label operator dot x, right? But the label operator then doesn't care about the sum, so I can push it through. So as an operator, it goes through the sum. I have that. And for a lot of purposes, we can actually kind of, in a sense of suppressing indices, we can just use a simplified notation for this guy where we suppress the sum. So we were thinking about this as a discrete sum. And we can always write out that sum if we get confused. But we could also adopt a notation where we suppress the sum. And for many manipulations, just like you might suppress some indices in a quantum field theory, that's perfectly fine. So and having this label operator makes it easy to do that. So if you have, for example, field products, say I had two fermions, we're trying to make the notation work for us as nice as possible. Well, if you have a sum of momenta and then it's exponentiated, then if you have a product and it's a product of exponentials, then it just becomes the sum in the exponential. So this is true if we do it for two fields. Right? I'd have the label operator acting on this guy and that guy. And if I were to write out this twice with two sums, then because the product of those two exponentials can be just written as a single exponential, this is true. So this guy acts on both fields. So in this sense, the notation is friendly. And what this phase factor here is really doing for you, if you think about it on a whole product of fields, it's just when you Fourier transform giving the label conservation. Okay, so there's going to be this kind of overall e to the minus I p dot x, and it's just sitting there to conserve momenta in the label space. So that's its purpose.